Okay, well, thanks a lot for that very nice introduction. So I'm going to tell you something very curious that goes against many things you've heard. So I'm sure you've heard these kinds of statements repeatedly. Einstein's theory of general relativity is incompatible with quantum mechanics. It's actually kind of a silly statement. That statement actually isn't true, but never mind. But people say that. But usually what they really mean is something else. What they're usually referring to is all point-like quantum field theories of gravity are divergent and nonrenormalizable. That's the more technical way of saying that same statement. So let's have a look at where these statements come true, where these statements come from, and whether they're true or not. So the logic behind those statements is actually pretty simple. It's just a simple power counting. If we look at a theory of quantum gravity, where we usually describe it by Feynman diagrams, and these diagrams, they represent an expansion in h bar. So every loop, I'll be talking about loops, they refer to an expansion in h bar. Every loop represents an h bar. And we can compare a theory, Einstein gravity, to a theory, gauge theory. So that would be a theory of the strong interaction or electrodynamics. Weak interactions, those are all gauge theories. And we can just compare using the fact that Newton's constant is dimensionful. That's the coupling constant that appears in the diagram. So just by simple dimensional analysis, if you have a dimensionful coupling constant, you need something else to make up for the dimensions. And that's these momenta here, these loop momenta. They're called loop momenta. And then according to the Feynman rules, you're supposed to integrate over them. And if we compare these two theories, Einstein theory against the gauge theories, using the fact that this is dimensionful, this coupling constant, and that coupling constant is dimensionless, well, this needs more powers of momentum to make up for the dimensions. If there's more powers of momentum in this numerator here, when you do the integral, this loop integral in the Feynman diagram, then you're going to get a bad behavior just because at high energies, large momenta, these are 4 momenta here, but anyway, at high momentum, you're going to get an integral that behaves poorly. And that's the basic argument that says that Einstein gravity is poorly behaved in the ultraviolet. By the ultraviolet, I just mean high energy behavior of these integrals. Now, you can get very sophisticated. There's all sorts of things you can do and write very complicated papers. Hundreds and hundreds of papers have been written on this. But the bottom line, this is the argument. You can get more sophisticated, but you're basically in trouble because Newton's constant is dimensionful. Now, these types of arguments, they're always like a bound, because you pick some diagram or there's some argument you're making based on some dimensional analysis of the integrals. You say, okay, look, this is the way it behaves. It's got to be poorly behaved. But what you need to worry about is maybe there's a hidden symmetry. And I don't mean like hidden in the theory. I mean hidden from us humans, right? That we don't know about it. And that what actually happens, if you add up all the pieces, it's actually very well behaved. Right? And that could happen. This is no secret. Everybody knows this, but it seems unlikely. Now, we're going to be talking about a theory called n = 8 supergravity. And these types of theories are very good to look at because this extra symmetry, the supersymmetry, it helps a lot in 2 ways. One is if you have supersymmetry, it's actually well known that the supersymmetry makes these ultraviolet behaviors better. So that's good. If you're going to try to find a theory that's well behaved, you should look at the ones that you know are better behaved. Pick the one that's most likely to work. But something much more important is if you have a lot of symmetry, you can exploit it, and you can then do these calculations. You can study these theories. They're like toy theories for the real thing, for the real world. If you can't make one of these theories sensible, then you could say there's no hope for making the real theory of gravity sensible. And in fact, these types of theories, these supergravity theories, they may look a little complicated. You're adding 254 other states besides the gravitons. So you say, that's really complicated. But you're adding them in just a special way so that they come out simple, so that the final answers come out simple. And in fact, these types of theories, they were in the 70s and 80s, they were considered to be the best hope for finding a unified theory of gravity with the other forces. That was before string theory came into play. Well, it's when people gave up hope of these types of theories. And then string theory came along. Now, the reason why we're interested in this, whether a theory is finite, it's actually not so important that it's finite. What's really important is the symmetries. If the thing comes out finite, there's a reason for it. It's not an accident and something very deep and important. And in a sense, that's the thing we want to discuss. And there's a lot of questions you can be asking, but in a sense, we're asking a very simple question. You have this theory, this n equals 8 supergravity or some other theory of gravity along those lines, and you're just asking, is the theory finite in the high energy, or is it not finite? Right? And it's not a question of philosophy or debate. You know, people debate all this stuff, but it's not for debate. It's something that you want to calculate. You just want to know what the answer is. Yeah?
So what's the benefit of 8? Why not 9?
Well, because 8 is the most you can have. Anything more than that, it would not be a theory of gravity. There would be other forces in there. So it just happens to be from the group theory that n equals 8 is the absolutely best one. This is the best one to pick. It's called maximal supergravity. Okay. If we could do 9, we would do 9, but 8 is as high as you can go. Okay, so in some sense, this is the best of the theories, the maximal supersymmetry. Okay, and in the 80s, by the middle of the 80s, or beginning of the 80s, people were starting to lose hope. I mean, so here's some quotes from what people were saying in the 80s. If certain patterns that emerge should persist in the higher orders of perturbation theory, that's that loop expansion, n equals 8 supergravity in 4 dimensions would have ultraviolet divergences starting at 3 loops. Basically saying that the theory is not going to be a fundamental theory, and we have to go look at something else. Now, but notice very carefully, they don't say the theory diverges. They say that's our best guess based on certain patterns. Right? And here's another one. This quote I like a lot. I use it a lot. It is therefore very likely that all supergravity theories will diverge at 3 loops in 4 dimensions. But then they say the final word on these issues may have to await further explicit calculations. That's what we're here to do. To actually find out what the truth is. Okay. But this has been the wisdom, because it's, as we'll see in a second, it's incredibly hard to do these calculations. Okay, here's another quote. This one I like a lot. Kind of an amusing one. This one's from Hawking. So this is in 1994. He said, it is not clear that general relativity, when combined with various other fields in supergravity theory, he was actually thinking about n equals 8 supergravity, cannot give a sensible quantum theory. Reports of the death of supergravity are an exaggeration. I deduce from that he read Mark Twain, or he knows about Mark Twain. But anyway, one year everyone believed that supergravity was finite. The next year the fashion changed. That's string theory, of course. And everybody said that supergravity was bound to have divergences, even though none had actually been found. And which is true. Now you'd say, okay, why didn't people just do the damn calculation? Well, there's a little problem. So it's 3 loops. You know, people said, look, you can't have these problems will start at 3 loops. And you just look at what you're facing when you try to do one of these calculations. It's completely out of control. So there's actually just one diagram in some specific gauge, if you know what a gauge is. But if you just look at that diagram and you see how complicated it is, it's hopeless. And you're talking 10 to the 20th terms at 3 loops. So you come down to 5 loops. It's ridiculous. 10 to the 31 terms, which I might point out, is more terms than atoms in your average graduate student's brain. Right? So it doesn't fit. You can't do the calculations. Anyway, if you're an expert, you can start debating me. Oh, you should have used superspace. You should have counted differently. Doesn't matter. Count it any way you want. The conclusion is the same. The calculations are hopeless. You cannot do them using ordinary techniques. And this definitely seemed destined for the dustbin of undecidable questions. It looks like it diverges. As best as we know, it diverges. But, okay, we don't really know. But who cares? Because we can't do it. Okay? Well, to show you an example of the progress, it's actually today, that's those same calculations. If we're looking at n equals 8 supergravity, the problems are completely doable. This 3-loop one, as a trick, I sometimes do this on the blackboard at a summer school. Let's go work out 3-loop supergravity, because it's actually very few terms. And I'll show you the secret of how this is done, what the magic is of simplifying things. So one of the points of this colloquium. 5 loops, I think that was impossible. It's now doable. We've been having some technical problems with this, but I think we're past that now. But this is definitely in the class of things that are doable, even if it hasn't been done yet. Okay, and you can ask, is there some unaccounted for structure? You know, people have these arguments. And usually the arguments are based on hubris. It goes like this. I know everything about supergravity, right? You know, maybe I'm the inventor of it, or I know everything about it. Nothing is hidden from me. And based on everything we know, this is the way it behaves. But the problem is, suppose there's something you don't know, an unaccounted for structure. Is there a structure in the theory? Is there a hidden symmetry in the theory? And if that exists, then the counting you have, the power counting, could be wrong. Right? And in fact, there is such a structure, which I'll show you. Something that's actually kind of amazing that it exists. But before we attack gravity, let's take a little detour. I'm going to wander very far away from gravity. I'll talk about collider physics, scattering amplitudes. Scattering amplitudes are something very fundamental to our ability to unravel nature. A lot of what we know comes from the particle colliders. This is a bird's eye view of CERN. And the basic idea is you smack together protons, or really you're trying to smack together the quarks and gluons, and then you try to study what the interactions are. And that's on the theoretical side. The scattering amplitudes are something fundamental that we have to understand in order to extract the new physics, or the interesting physics. Now, this is a vast subject, and I'm not gonna even scratch the surface of it, but just give you a little flavor of some of the ideas that we use to understand these scattering amplitudes. And these same ideas, they're going to carry over to gravity. We're going to study gravity using these ideas of the scattering amplitudes. Now, back in 1948, Schwinger had done this calculation, the anomalous magnetic moment of the electron. I wrote a Feynman diagram here, but I can assure you he did not use a Feynman diagram. He did it a different way. But anyway, it was affected in a modern language. We'd say it was this Feynman diagram. If you go 2010, what kind of calculation could you do using Feynman diagram technology? You're talking about a process where the gluons that are inside the proton, they go into a W boson, and then, let's say, 2 quarks, which then turn into these sprays of particles we call jets. And this would be a typical calculation. You're probably a little surprised. Well, back in 1948, you know, Schwinger just did it all by hand. Today, we have our supercomputers and all fancy ways of doing it. You know, how come, you know, we're only 2 legs? You know, there's only 2 external legs beyond Schwinger, 2 or 3, or, you know, why aren't we 100 legs beyond Schwinger? What's all this computer technology doing? Well, there's a little bit of a problem, which you can actually see very quickly once you start looking at how these scattering amplitudes go. So the next most complicated process beyond, let's say, like 2 protons into 2 jets, which come out of these gluons, would be where you have 2 gluons from the protons turning into 3 gluons. I mean, that would be like a next most complicated process. And you say, OK, let's go work that out. And you can open up your textbooks, and there's rules. You follow the rules, and you calculate. Anyway, this is just actually a small piece of the result. And that's like, one of the simplest processes you can write down. And the thing basically goes completely out of control. If you're wondering what's contained in here, there's momenta. These are 4 momenta. There's polarization vectors. And then it's some giant mess arranged in some complicated way that's actually very hard to understand. So what happens very quickly is the calculations kind of spiral out of control, even in this relatively simple case. But just a little taste of how you can clean things up is use better variables. They're called helicity states. This is just like circular polarization of light. It's also called Chinese magic. The kind of magical how it works, but anyway, these people worked out a formalism that we use today. So these things, they're spinor inner products, if you're wondering. But anyway, this slide here, that's contained here, contains the identical information contained on that slide. Actually, this contains more information. We got the complete answer, written out in a certain way. So that's like one lesson is if you understand the right variables to use, these spinor variables, then all of a sudden what looked like something impossibly complicated, just a mess with no structure, no understanding, all of a sudden you see this pattern. Right? There's a pattern. Now, these types of diagrams, like these that have, we call them trees. So that's the lowest order of the perturbation theory in terms of H-bar expansion. So these are the simplest, and then comes the loops. So this would be some loops diagram you have to do. And I just actually wrote down one term. Never mind, there's thousands of other terms. I actually picked the most complicated one. Just one integral you have to do. Right? And what happens if you do this, and the people, by the way, who do this for a living, you give them this problem, they'll do it in 5 minutes. They have all the software. Computers can deal with this stuff. But this one is the very simplest one of the problems. Now, if you do that integral using standard techniques, this is what happens to you. That, in fact, is the answer. If you're wondering what the heck this mess is, you see these gaps here? So right at the end of a gap is an integral, and that's a known integral, and that's a coefficient in front of the integral. So it's an expansion in terms of a basis of known integrals. Now, OK, this, you say, OK, that's kind of bad. And this thing is actually a lot worse than you think, because it actually induces numerical instabilities in your answer. So you can't even numerically evaluate this thing. But if you're looking for some real pain, what you do is you take this mess, and you scramble it into the previous mess. Right? You increase the number of legs, and now you're talking serious pain. Right? So, and that's essentially why the brute force hasn't pushed, like you could say, like basically solved the problem. Okay. Now, the basic idea for attacking this kind of mess has to do a lot with Einstein's relation. Remember, so the E squared minus P squared is equal to M squared. That's Einstein's relation. But if you look at any Feynman diagram, the basic rules of it, you'll see very quickly that especially at loops, but also at trees, that Einstein's relation is not satisfied by these particles. We call them virtual particles. That's like a fancy way of saying they're not physical. Right? The things that you see in here, they don't represent physical particles because they don't satisfy Einstein's relation. Now, if you don't do things in a way that's physical, like every step is physical, you're calculating all these unphysical quantities, you know something bad's going to happen to you. So the way it works with Feynman diagrams is the fact that the pieces that you're evaluating, these diagrams, are unphysical means some bad thing happened. You're calculating all this garbage. And then at the end, you take all the garbage and you add it up, and all the garbage cancels out, and then you get a physical answer. But in the middle, it was full of garbage. What you need to do, if you want to clean up the perturbation theory and not lead to catastrophic pain, is what you have to do is organize things so at every step you're only calculating physical quantities. We say gauge invariant quantities. And the basic lesson is don't violate Einstein's relation. Okay. And there's a whole formalism developed over the years. So this was with my collaborators, Lance Dixon, Dave Dunbar, David Kossauer. And also there's other developments I'm not going to talk about at tree level. That was mainly from Cachazo, Brito, Feng, and Witten. With the same basic ideas is when you're trying to build a new amplitude, let's say at one loop, like there's a loop in here, what you do is you only use physical quantities, the tree level, in your calculation. And you have to do this, you need a way of doing this systematically. A lot of this was understood in the 1960s, but not all of it, like the generality of how you're supposed to assemble things to build any amplitude, essentially any type of Feynman diagram, but we're not going to use Feynman diagrams or sums over Feynman diagrams. This you could say it's like a trick. It's like a trick, if you wish. We're really trying to calculate Feynman diagrams, and everything we do, of course, we have to make sure that it always reproduces what you would have gotten from a Feynman diagram calculation had you done it by Feynman diagrams. Of course, we can't do it by Feynman diagrams because it's technically too complicated. At least in these, at least in the complicated cases. State of the art, we're trying to push the boundaries. Then you can't do it by Feynman diagrams. And these techniques really work. So this was all developed, all of this technology and way of thinking about things actually had to do with collider physics, quantum chromodynamics, the strong interaction, trying to solve problems there. And I can show you, there's a very nice slide. I stole this from Gavin Salam. So about what's called the next to leading order revolution. Next to leading order refers to the higher order of perturbation theory in quantum chromodynamics that you need for collider physics. So it talks about the types of processes you could do. So in the 1980s, people could do two particles into one, and that was like a big deal. Then 10 years later, 2 into 2, and that was a big deal. Another 10 years, 2 into 3. Okay, and here we are. This was around 2010. People finally understood how to do 2 into 4 starting to use unitarity means these modern techniques. Traditional means using Feynman diagrams. And of course, you're looking at this and you say, what revolution? I don't see a revolution. It took you 10 years. Well, the revolution is here. That's on the next slide. Oops. How long did it take to go to the next level? 2 to 5, 1 year. And then, it just continues 2 to 6. So people now say, it's probably not exactly true, but anyway, they say that next to leading order is a solved problem. Now you can really go very far. And that's a revolution. It's no more 10 years. Just one after another, people have done all sorts of automation. So that's really good. Oh, and there's even a better part. And this is the best part. It actually works. You can compare to experiment. So you're doing fundamental calculations in quantum chromodynamics. So it's not, you're not tuning anything. Sometimes you have to tune against it. No tuning, fundamental theory, compare it against experiment, and it works. Okay. So this basic idea of thinking about perturbation theory in this different way, not using the Feynman diagrams, but trying to rewrite everything in terms of quantities that are physical, not gauge dependent, is something that's proven to be very useful. And in fact, we're going to, what does this have to do with gravity, you're asking? We're going to apply the same ideas to gravity. So let's go back to gravity. So let's compare gravity to gauge theory. So gauge theory would be, any like a QCD, quantum chromodynamics, weak interactions, electrodynamics. Let's compare the two theories. So the way you do gravity, sorry, when does this thing finish? Oh, okay, good. Okay. Okay. So the way gravity works is you take the Einstein action and then you expand it around flat space. So this is called the metric. That's flat space. And this deviation from flat space, it would be what we call the graviton field. And you plug it in there. If you try that, you will discover a pretty gigantic mess. You're going to get all sorts of interactions where three gravitons interact, or 4 gravitons, or 5, or 6. It's an infinite series of this. And it's actually quite complicated. I'll show you little pieces of this. I'll show you what this thing looks like. It's basically a catastrophic mess, as we'll see. And let's compare it to gauge theory. In gauge theory, if you look at it, you'll say, well, that's, there's some complicated quantum field theory, but there's a 3-point interaction, a 4-point interaction, and there's not this infinite mess. So you'd say, well, this theory and that theory, the two theories, they don't look related. They look like maybe they don't have much to do with each other. Okay. And certainly gravity is much, much more complicated than a gauge theory. Just to give you a little taste of the difference between the two theories. This is gauge theory. Any of you graduate students who are in particle theory, would know what this vertex is. This is the Yang-Mills. This is called the Yang-Mills vertex. It's basic in electroweak theory and basic in quantum chromodynamics. It tells you how 3 gauge bosons interact. It's a little complicated, but it's not terrible. There's this coupling constant G, and this thing is called the color factor. So that's just a group theory factor that tells you how the different types of gluons, how they interact. There's some matrix there. Okay. Let's compare that to gravity. So if you look at the 3 graviton vertex, I've written it out here, but I wrote in like a compressed notation so I can actually get it on the slide. So there's a sim here, and that says you're supposed to symmetrize in let's say nu and beta, alpha and mu, and you're supposed to symmetrize this. So there's 8 symmetrizations of these indices. Then there's, like you see this P6. The P6 refers to 6 permutations. It's 1, 2, 3, and there's 6 permutations of this term that you have to include, and you add it up, there's about 100 terms. So that's really complicated, the way three gravitons interact. And if you were a graduate student and your advisor told you, oh, we need to do this problem in gravity, and showed you this vertex, if you're clever, you're going to say, oh, that's very nice, but I'll go work on a different problem. This is not a happy situation. Gravity is a nasty mess. That's what anybody who touched gravity would conclude. But in fact, people were looking at it the wrong way. The correct way to look at it in terms of for scattering amplitudes is you want to go on shell, Einstein's relation. You want to impose, when I say on shell, I mean Einstein's relation. You impose the on shell conditions on the vertices, on these gravitons here, 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 here. You put them on shell. In the Yang-Mills theory, the gauge theory, not too much happens because it wasn't that complicated. You can simplify it a little bit, but never mind. In Einstein theory, the thing collapses. Boom, just completely implodes, and it has this very curious structure. See, it looks like 2 copies of that. See, there's 1 copy, and that's the second copy. And I just cross out that color factor and just take 2 copies of this kinematic factor. Okay, so in fact, these things look like they're related if we think about it in this on-shell way. It looks like maybe we can take advantage of everything we learned from QCD and quantum chromodynamics and apply it to gravity. Maybe we can do that. And in fact, something very important, which I'll just make a comment on, which is actually kind of amazing, something very crucial, is these modern techniques, this on-shell way, it turns out that all the information for building the entire, it's called S matrix, the entire scattering amplitudes, all of them resides right on this page. So if I want to understand how 1,000 gravitons scatter, suppose I was interested in that for whatever reason, then the information of how to do that is right here. Right? And for those of you who know, let me just throw out a word. It's called BCFW recursion at tree level. And then we use that method I talked about, this unitarity method, to build the loops. Okay? So everything is there. So in fact, it's obvious these two theories really know about each other. So now I can correct something. So I had a wrong transparency. So let me fix it. So the wrong transparency, I mean, it's true if you take this Lagrangian and you plug in the fluctuations, the graviton field, you do get this infinite mess. But so what? We never use that infinite mess to calculate anything, right? Because it's not part of the way we do things anymore. In fact, by the way, Feynman kind of understood this. Well, what he understood is that all of this could be derived from that. You could say the next step is to say, we don't even need any of this. Okay? And in fact, you can do the same for gauge theory. You don't really need this, but that's not a big deal. But in fact, the only thing you need are these two pieces. And this piece is just the square of that, or the other way around. This piece is the square of that. Right? So in fact, gravity seems no more complicated than gauge theory. And in fact, the two theories look very closely related if you look at it the right way. And that we're going to exploit. Now, that's just the beginning. It turns out that the secret of quantum gravity, or certainly for scattering amplitudes, it actually has more to do with gauge theory than it has to do with gravity. That seems like a strange statement. But let's take a little detour into gauge theory. And I want to show you something really weird about gauge theory and something we're going to exploit. We're going to make use of something. A little accidental observation. You know, we happen to notice something. And the thing we noticed, it's like a little curiosity, which is the following. So here's 3 gluon vertex. So this would be in quantum chromodynamics, exactly what you'd use to understand strong interactions. There's a kinematic factor here. It depends on form momenta. There's a coupling constant. And then there's this, we call it color factor. That's just a matrix that tells us about how the different colored gluons, the color charge, how they interact with each other. It's just a matrix of numbers. It's nothing fancy. Now, these color factors, they're based on what's called the Lie algebra. So there's a commutator. Actually, rotation group would be an example of Lie algebra. So nothing too fancy. Now, what do these color factors do for a living? Well, they're based on Lie algebra. And what Lie algebras do for a living is they're called structure constants. They obey what's called the Jacobi identity. That's what a Lie algebra does. Okay, so nothing fancy there. Now, we're going to do one little trick. Let's just take some Feynman diagrams. And so nothing fancy. So you can go home and check what I just said if you like. You know, if you want to take out the Feynman rules, you can check exactly this thing I'm showing you. I'm going to take this 4-point vertex, which is there's missing propagator. This line here represents 1 over s or 1 over t or 1 over u. There's a line there. This one's missing. And so I just put it back. So if I see in this diagram a color factor that looks like this one, I just multiply by s over s. I put back the missing propagator. And I'm going to write the amplitude in a simple way. There's a numerator. The numerator, kinematic numerator, comes from the algebra of the kinematic factor here. There's a color factor. Color factor is like one of these. And then there's a Feynman propagator. And I write the amplitude in this way. And then you can go home and check this. And it doesn't matter exactly how you do it, as long as you put these gluons have to be on shell. So they have to satisfy the Einstein relation. And if it satisfies the Einstein relation, you'll discover that these numerators happen to satisfy exactly the same identity as the color factor. And you might ask, who ordered that? Where did that come from? I'm not going to tell you where that comes from, because I don't actually know. But never mind, it's just a little observation. Now you might say, well, that's very amusing, but what are you going to do with it? Well, we'll get to that. Well, maybe before you ask what are you going to do with it, you might ask, does it hold in general? And the answer is yes. It holds in general at tree level. So there we've proven it. It's actually a tree at higher, let's say a 5.5 gluon amplitude. It's more complicated. If you went home and tried this, it would not work. You have to very carefully arrange, move pieces between the diagrams in just the right way for this to work. So the statement now is a little, there exists a rearrangement of Feynman diagrams such that once you write the amplitude, the scattering amplitudes in this form where you're writing in terms of these cubic diagrams, then for every Jacobi identity, colored Jacobi identity, there's a corresponding kinematic numerator identity. One-to-one correspondence between these two concepts. And you're probably asking, what does this color have to do with the kinematics? Well, I'm not going to tell you that, because I know a little bit about it, but I don't really have the answer for that. We're just observing this. As you say, that's pretty weird stuff. Anyway, it's been proven in many different ways, using string theory and other types of techniques. This thing has been proven repeatedly in various ways. So you say, okay, that's very amusing. But what are you going to do with it? Well, the answer, what you're going to do with it, is the secret of gravity is actually on this page. And the secret is the relationship between a theory like quantum chromodynamics. Right? We're going to write it in this form, the color factor, numerator factor, these Feynman propagators. And what we're going to do is write it in a way that the numerators have the same algebra as the color factors, that they satisfy the Jacobi identities. We're going to figure out how to do that. So once we've done that, magic, this is the key magic. If you want Einstein gravity, you just take the color factor and you replace it by a numerator factor. It's magic. This magic happens to be proven magic, but we'll get to some unproven magic shortly. And you say, well, who ordered that? Well, I don't know who ordered that, but this construction, it's now known as double copy construction. And the one thing it definitely does is it cries out for a unified description of the sort given by string theory. Okay, this doesn't prove string theory, but it smells a lot like string theory in the sense that these two things are intimately connected. And in a very detailed way, that these numerators, see that these numerators, they're the same as those. That's the key point. It's not like different, right? So if you want to understand the dynamics of Einstein gravity, it comes from the dynamics of quantum chromodynamics. And string theory actually has that kind of property. The difference is we're doing it bottom up. We're just playing games with the Einstein Lagrangian, and we're just trying to understand gravity, and then we happen to observe this relationship. And what this definitely says is these two theories belong together. Okay, here's the fun part. Now, we want to do quantum gravity. What I was showing you a minute ago was tree level. That's h bar is 0. That's not quantum gravity. That's more like classical gravity written in a quantum way. But it's like semi-classical. But if you want to do quantum gravity and you want to understand ultraviolet behavior and you want to understand the symmetries of the theory, we need to be looking at these loop amplitudes. So it turns out that if you can arrange loop level such that for every color identity, there's a numerator identity. Let's suppose you could do that. That's the really hard part, by the way. But let's suppose you could do that. Then if you want to go at loop level from gauge theory to gravity, you just take the color factor and replace it by a kinematic factor. If it sounds like magic, the reason is because it is magic. Okay, the true magic is that you can do this, that this is a possible way to do that. And that we don't have a proof for. In fact, in some cases, we've had some serious trouble getting this to work. But once you have this, then this you can prove pretty easily, this part, that you do get gravity out. Yeah? So the integrand, the thing you're supposed to integrate, it just follows from gauge theory. Yeah? Yeah? Someone?
It's a naive question. Is there any physical justification for this for this?
Yes, there's bits and pieces of this are understood. In certain cases, we know exactly why it happens because there's a Lie algebra, infinite dimensional Lie algebra behind these numerator factors that you can actually write down explicitly. The unfortunate thing, that's only in certain cases, so there's not a general proof. At this point in time, there's no general proof of this. It's just known to be true. We've proven it at tree level, and that's an observation. Now, one of the fun things, like a difference between like a mathematician and a physicist, as a physicist, we don't care if we have something proven. We don't care if we understand it. What we really care about is can we use it, okay? And that's what we're going to do. So we don't have a complete understanding of this, but we're going to exploit this. Yes, this is definitely related to that. You could say, well, this is a hidden structure. So you're imagining that you're trying to make statements about this is the way ultraviolet behavior of gravity is. This is the way gravity behaves. And you don't happen to know this little fact that these two theories are related. You probably should worry. I did a little detour. I just can't resist. Let's just take a little detour. So there's this idea that in the scattering amplitudes, we have plenty of evidence that the two theories are related. You get one from the other by this double copy procedure. So gravity follows from gauge theory by this double copy procedure. So you might ask a reasonable question, what about other solutions, like maybe black holes, or what about classical solutions in general? Can you do the same thing? Because now we know these two theories belong together, right? So wouldn't it be really cool if you could do this in general? Well, where do you start? I mean, you need an example to actually see if this is reasonable. So obviously, the place to start is the coolest place possible, which is black holes. That's the solution you want to look at to try to understand if this is possible. And the answer is it is possible, at least in certain cases. The black hole solution actually maps to an electrodynamic solution of the point charge. And that's based on using some special coordinates. Actually figure out what the relationship is not so trivial because these theories have you call them an ambiguity called gauge invariance. And if you don't do things right with the right coordinates, things can be very, very obscure. But with the right coordinates, in fact, it's kind of obvious what the relationship is. There's the metric, the Schwarzschild. So this is the black hole solution written in these coordinates. And you just kind of look at it. See, there's this phi here. It's the same one you find in electrodynamics. And there's some vector k that's part of the solution, and you see two copies in the graviton solution. So that was worked out by these people. In fact, there's many other solutions now, like rotating black holes. Here's a cool one, radiation from accelerating black holes. Now, so far, this is just examples. Right? Of course, what you'd really like to do is do this in general, try to rewrite general relativity so that it's actually two copies of gauge theory. And the reason why you want to do that is because gauge theory is a lot simpler than gravity. Okay, now that was a little detour. Let's get back to the real business of let's let's now use these ideas. Let's see what applications we can use of these ideas. So that's using these on-shell methods, and then also this double copy construction. So actually, the first calculation we did along these lines, so this is before we understood this double copy construction, but we used this unitarity method. That was back in 2007, where we were really sure that what people had said in the 80s was not correct. That we said there'd be a 3-loop divergence. It just didn't look right. So we had the technology, the ability to do the calculation, sat down, did the calculation. Long story short, it's in fact very, very finite. Not only is it finite in 4 dimensions, 4 space-time dimensions, it's finite all the way to 6 dimensions. So that's an extremely finite theory. Okay? Now, if you ever do one of these calculations and you get a result like that, you should not be surprised at the reaction. So what people are guaranteed to say is, oh, that was a great calculation, great job. But you're going to have trouble at the next loop order, of course. And there it is. There's the paper. 2009, this is one of the papers, said exactly this. This is from their abstract. In particular, the ... is whatever methods they used. Suggests that maximal supergravity is likely to diverge at 4 loops in d equals 5 and at 5 loops in d equals 4. Now, you notice it's written, they say suggest. And the reason why it suggests is because these power counting, whenever you're doing, I know all the symmetries, and then you power count, you can never prove there's a divergence. You just say it's likely there's a divergence because I don't see any reason why it's finite. So, of course, when we read that paper, we got excited. I made a bet with my friend, Kelly Stell. That's actually the bottle of wine. It's an Italian Barolo. And we had the tools to collect the wine. So we did the calculation. And the bottom line is that, in fact, it is very finite once again. Whatever statement they made was not correct. There's more symmetry, clearly. Okay. Now, of course, by then we had some experience with this, so we were not surprised when the reaction was, that's a great calculation you did, but you're going to have trouble at 5 loops. Now, by that point, a lot of people got interested in it because something was going on. We proved that there was something interesting going on. So a lot of people looked at it. There's actually quite a collection of distinguished people. Actually, there you see Michael Green, inventor of string theory. There's Dan Friedman, inventor of supergravity, and many other distinguished people got interested in what's going on here. So what they argued, and it looked actually kind of decisively argued, that there would be trouble starting at 5 loops, right, at the next loop order, because they could find no reason why the thing would be finite. And even worse, they explained everything we found. Everything was explained in terms of a symmetry. And the symmetry wasn't so profound. It was really just supersymmetry and other well-known symmetries that were used in this to understand this. And so if you were a reasonable person, given the fact that everything was explained, you would say that it probably will diverge at 7 loops, and there will be trouble at 5 loops. That's what the consensus of the field. Now, while they were at it, they're actually very kind to provide other information. For example, well, here's n equals 8 supergravity should diverge at 7 loops in 4 dimensions. That was the prediction. Okay, here's an amusing one. 5 loops in d equals 24/5. You'll say, what's d equals 24/5? I say, don't worry about it. We're theorists. We can do whatever we like. So anyway, and never mind exactly what that means, but anyway, it's some prediction of how the theory behaves. And then n equals 4 supergravity, half the supersymmetry, less supersymmetry. It makes the theory way more complicated. On the other hand, it lowers the interesting loop order that we could work at. Okay, so that's 3 loops. N equals 5 supergravity is supposed to diverge at 4 loops. Okay. Oh, and by the way, there were quite a few people interested in this. That's my friend Sheldon. Look at his board there, the whiteboard. Anyway. Okay, but me not being a reasonable person, I took this as an opportunity to make bets because there's one little problem with what all these arguments were saying, that if you were to look at the actual theory and how parts of the theories, the parts that we could calculate, how it behaved at very high loop orders, it was not consistent with a consensus. Now you could say it's just an accident, but I'm not one to believe that there's accidents like that. It just did not seem right that the consensus was correct. So I took it as an opportunity to make some bets. So here are the bets, two bets. One is at 5 loops and d equals 24/5, does n equals 8 supergravity diverge? Okay. Another bet at 7 loops and d equals 4, does n equals 8 supergravity diverge? So 5-loop bet I made with my friend Kelly Stell. So I live in California, so I put up a bottle of California wine saying it won't diverge. Unfortunately, my friend Kelly, he lives in England at Imperial College, and he put up a bottle of English wine. And he said it will diverge. Okay, I also have a bet with David Gross on, he wouldn't have anything to do with his 24/5. You know, it's like, so that was the only bet I could get with David Gross, 7 loops. Yeah. Now, we made this bet because we thought at the time that this would be the easiest calculation to do. But it turned out that that was not true. There were some problems with this that made it difficult to calculate. But there's another theory. Okay, let's go back. Right here, this one. N equals 4 supergravity should diverge at 3 loops and d equals 4. And that one turned out to be completely doable. So we just did the calculation. Now this relies heavily on this double copy construction, because this is a very complicated theory. And if you don't reduce that theory to a gauge theory, it's just impossible. You can't do it. But anyway, using that double copy construction, we were able to do this theory. Actually, this turns out there's 12 diagrams. Here's a list of the diagrams. You look carefully. There's some weird numbers like zeta. That's zeta of 3, zeta constants, and these 1 over epsilons, those are the divergences. They represent divergences. And if you take all the pieces and you add them up, what do you get? Well, you get 0. There's no divergence. Now, one very unfortunate thing about this is by the time I realized I should have made a new bet, we already had the answer. And so I was feeling kind of guilty, you know, to actually write to my friend Kelly and say, let's make a new bet when I already knew the answer. Should have been quicker to say, oh, let's make a bet. But anyway, there's no symmetry explanation, no standard. So this one is a counterexample to the consensus. I mean, this basically says the consensus arguments are not correct because they predict divergences when there are none, or they're incomplete. I'm being recorded. I should not say they're not correct. I should say they are incomplete. Anyway, the implication of is incorrect. That's for sure. Okay. This is true, but despite a valiant attempt to actually do this. So far, there's still no explanation that's of the standard kind. Now, the way these cancellations work, they're not standard. They don't work the way it works in an ordinary gauge theory. There's something extra that's going on here. And what makes it actually very hard to dissect, or the reason why the standard arguments don't work, actually has to do with an interesting property of how the cancellations happen. Normally, when you apply those arguments that people have, what they're basically arguing is how one of these Feynman diagrams behaves. I mean, that's not the way it's phrased, but it's kind of equivalent to that. How one of these Feynman diagrams behave. But in fact, we can prove that there's no possible way that you can write one of these Feynman diagrams in a way that's Lorentz covariant, such that they are well behaved. The individual diagrams are poorly behaved, but you add everything up, it's well behaved. Right? And that has to do precisely with the reason why it's so hard to understand this, where the cancellation is coming from in the standard ways. And we call this enhanced cancellation. That's like a definition of what these extra cancellations are. And this is something we're actively trying to understand. Here's another example. So this one is actually quite a complicated calculation. For this, it's like industrial strength software to do this. This is a for loop, n equals 5 supergravity. And that calculation is broken down the super-Yang mill, so that's gauge theory, times another super-Yang mills. So you're effectively rewriting it as gauge theory. It's still for loop gauge theory is still pretty complicated to do. You need tools that come from the QCD community. So there's a program called Fire5 for doing these integrals. Also needed some help from our Russian friends. You know, when you get serious on this, you need some help from the Russians. Anyway, there's 2 Russians. So that's what the little 2 is. It's a father and son, a son team, by the way. Anyway, the bottom line is this is another example of that. And once again, it's a pity we didn't bet on this one as well. Although by now, you know, after we'd done that 3-loop calculation for n equals 4 supergravity, I could no longer make any more bets. Nobody would bet with me. But oh, that's weird. Huh. Uh-oh. That's really weird. Okay. I don't know what happened there. Now, there are actually divergences. You know, don't think like there's no divergences. This theory, this n equals 4 supergravity, it actually does have a divergence, which we found at 4 loops. It has a relatively simple structure, but there's something very strange about it. And that has to do with something called anomalies. And that's an idea where you have classical symmetries, but they don't hold at the quantum level. And what we found is that there's a connection between these divergences that we do find in this theory and these quantum anomalies. Now, that's pretty weird. And that's something that we've been trying to understand also in other theories. But the one thing that that's actually kind of interesting is that if you have supersymmetries more than 4, like not like n equals 5 supergravity or n equals 8 supergravity, these anomaly issues, they don't occur, right? So what's kind of curious is we thought by doing this calculation, maybe we discover a divergence. You kind of answer the question. See, there's divergences. But in fact, it just added more confusion, right? Because the divergences we find are not generic. They seem to be very special. You know, somehow specially tied to certain classes of theories, but not all of them. What's the outlook? Well, the main one is the reports of the death of supergravity are an exaggeration, as Hawking said. So this UV ultraviolet finiteness of supergravity, it was given up for dead twice. Once was in the 80s, and the second time was with a consensus opinion, where people said, look, it's got to diverge at 7 loops, this n equals 8 supergravity, but in fact, it's not so obvious what's going to happen. I don't know if this will lead to a completely satisfactory description of nature through supergravity, but at least it's something that people are looking at this possibility again. And I think we did uncover some interesting things along the way. Okay, so the summary is we've reformulated perturbative quantum field theory into a form that allows us to attack difficult fundamental problems. And the one I spoke about here was, is it possible to have a perturbatively finite ultraviolet, perturbatively ultraviolet finite version of Einstein gravity? We don't know the answer to that, but certainly making quite a bit of progress on there's this remarkable connection that we exploit. So this is our basic tool now for understanding gravity and perturbation theory, is this relationship between the color and the kinematics, which then leads to this relationship gravity as two copies of gauge theory. And then there's, we know that there's some mysterious cancellations that we haven't fully understood yet. And then wherever we do find these infinities, they seem to have a strange behavior. It doesn't look like, at least the infinities we found so far, they can't be in these theories like n equals 5 or n equals 8 supergravity. Maybe there's other divergences, but certainly not the ones we found. Okay, and the final summary is supersymmetric versions of Einstein's general relativity are surprisingly tame in the ultraviolet, and I think you should expect more surprises as we use modern tools to probe these theories. Okay, well, thank you.
So you're talking less about string theory, but how really, if you think about it, how do you put it like a duality between like color and kinetic string theory?
People have actually spent, I don't know, maybe there's 10 papers, 20 papers on exactly this topic of these ideas and how they connect to string theory. Generally, at least right now, these ideas are mostly used to reorganize string theory to make it simpler. But to extract, like the goods out, like to all loop orders, what's the behavior? That's, you could say, an open question for our string theory friends. But there's certainly quite a bit of work on that right now. In fact, we're having a workshop at UCLA next week, and our string theory friends are coming to discuss exactly those points.
So, concerning the cool part, where you have the black hole.
Yeah.
So I was kind of curious, the black hole has certain properties that are not obvious at least for particles. So where's the horizon?
That's definitely true. There is no, there's no, okay, so the way you should think about this is there's like a physics solution that has this property that it can be obtained from gauge theory, right? But then once you have the gravity solution, you're now interpreting it, like there's the metric, for example. You're interpreting the properties of the metric, and you're saying, oh, look, there's a horizon, right? But that's not the, that's a distinct idea from the fact that there's a mapping between these two things. Excuse me? No, not on the horizon. But it's even in this double copy construction. Let me get like another example of this. Of once we have the mapping, it doesn't mean that the physics interpretation, immediately you just copy it over. So when we do this double copy construction, let's say we take n equals 4 super Yang mills. That's ultraviolet finite. And then we take 2 copies of this thing that's ultraviolet finite, right? And then you might say, why can't you just deduce immediately that supergravity is not ultraviolet finite? And the answer is because you now have, you now have a solution. There's a solution, actually it's of the integrand, and then you have to interpret it. You have to integrate it. You have to do something to it, and then you get a different conclusion. So it's not exactly. You shouldn't think of it like a mapping of the physics. You should think of it as a technical observation that allows you to extract the physics of gravity from the physics of Yang mills. Of course, it'd be much cooler if we could do exactly what you want. That I would definitely like, but you take what you can get.
So for these enhanced cancellations, are you suggesting that there would not be a typical symmetry explanation for why the cancellations, or there has not yet been discovered?
Well, let me quote Michael Green on this. So this is before the enhanced cancellations, but he's saying if there were such things, then there would not be a supersymmetry explanation in the conventional sense. Right? And that's like the key part. So there is no possible way there's going to be a conventional explanation, but that does not mean that there isn't an explanation that follows from the standard symmetries. And in fact, I would argue that it has to follow, in some sense, non-conventional sense, from standard symmetries, because what defines supergravity? And then you'll say, well, what defines supergravity is we impose general coordinate invariance, and then we impose supersymmetry. So everything follows from that, right? So somehow it does follow, but it's definitely not like a normal type of explanation.